Hello everyone. So in this lecture we are going to talk about binary search tree operation. We have already discussed the definition of binary search tree, that what exactly is binary search tree, and now we will see that how the operations are performed in this tree. When I say operations means we are focusing on insertion, deletion and search operation. So let's start. So searching for a node in a binary search tree, this is the algorithm. So in order to search any element in the binary search tree, we need to provide the two parameters. So we have one procedure here. We are calling it as a search element, and tree refers to the root node, means we are providing the address of the root node and also the value which we are looking for. Now, if tree data, now tree is representing the address of the root node, and we have fields there. We have a data field and the left and right field. So data refers to the value, and left and right refers to the address of the left subtree and right subtree. So if tree data is equals to value, that means you have find the value which you are searching at the root node, and you will return this node that the value has been found, and you stop the procedure. Or if the tree is null, means the address which is passed as a parameter, if it is null, that means that the value which you are looking is not found. So you can say here that return, or you can say print not found. So if it is, if the condition is matching this thing, then you will return the node, and if you are getting this thing null, then you will say not found. Otherwise you will move to the next part. If value is less than the tree data, now the value which you are searching, if it is less than the value stored at the node. When I said tree data, means this is the actually the address of the root node, and the if that value is more than the value, that means you need to move to the left subtree, because we know in the binary search tree all the lesser value than the root node is existing at the left subtree, and all the values more than the root node is actually existing at the right subtree. So the value which you are searching is less than the root node value, then you have to search in the left subtree. So what we are doing, it will return search element tree left well. Now one thing to keep in mind, we are doing here recursive call. So this is our procedure search element, where we are passing the root node address and the value which we are looking for. Now we are again calling the search element, the same method is being called, and here we are passing one address, and this is the address of the left subtree and the value which you are looking for. So what is actually happening, this is the scenario. We have passed the address of this node, and if the value is found here, you have to stop. If the value is not found here, then you will be comparing the value which you are looking is less than the value which is existing here or not. If the value which you are searching is less than the value at the root node, then you have to move to the left subtree. So what is happening, you will be moving to this part, and now you have to search in this tree. Now this tree is being passed. So when you are passing this tree, you are passing the address of this node, and this is becoming as a root of this entire tree. Again you will do the same thing. You will check that the value which you are searching is existing here or not. If it is existing, you will return the value. If it is not existing, then you will check that what is the status, it is less than or more than. Now if the value which you are searching is less than the tree data, then you have to call recursively the same procedure with the left subtree. If the value which you are searching is more, so either you are getting this part, means if this is not true, if this is not true, then you go to the else part. Else part means your value is more than the data which is stored at the root, then you have to call it the same procedure recursively for the right subtree, that means for this part, and then you keep on doing. And if you are, now how you will stop from this, what is the exit point? The exit point is either you get the value at the root node, or you are reaching to the situation where tree equals to null, and you will say it is not found. So We will take one example to understand in a better way. This is the algorithm, and the same algorithm we will be applying in one example, and we'll see that how this algorithm will help us to search the element in the binary search tree. Okay, so let us take one example. Okay, so this is the algorithm that we have discussed, and just we will write one more expression here. If the tree is equal to null, then we will write print not found. Now keep in mind, this is not a program code because we are not following the syntax. This is just a logic, and you need to use any programming language and use to take care of the syntax also when you are implementing this thing. Okay, so this is the tree given to us, and we are interested to search any element from this given tree. Let's say we are interested to find the value 59. So how to search the element? Now, one thing to keep in mind, that BST is an ordered tree where the left subtree is having the value less than the root and the right subtree is having a value less than the root. So we have to always start from the root, because if you look at this, so we will pass the root address and the value which you are looking for, 59. Now, so this value has been compared. Is this null? This value is not null, means now what is the meaning of null? Null means when this address is null. Address is null means either tree does not exist. So this pointer contains the address of this node. That means we already have a tree. If we have the value null here in this pointer, that means the tree is not existing. But in our case, this tree is not equals to null, but it contains some value, so it will check that the value which you are looking, value is 59. So 59 is more than or less than, so we will go here. If value is less than the tree data, so this is tree data, the value is not less than tree data, so you go to the else part. In the else part, what we are doing, tree right, you have to pass the address of this node. And how you can pass? Now this is your actually the node. This is your left part, this is your right part, and this is your data part. So we are comparing uh, this value with tree data. So in our case, actually the value is more than tree data, so it will pass the tree right. Tree right means the address of this node. Now actually you have to work on this tree. Now again, it's a recursive call, so you will check, is this null? No, this is not null. Already we have a tree. So what will happen? It will check the value which you are searching is more than this or not. So it is more than this. You again pass the right subtree. Now you have passed this thing. Means you have to work on this. Actually, you have passed the address of this right node. Then again, is this null? No, this is not null. So what will happen? It will check the value which you are searching is more than this. Yes. So you will again pass this thing. Now again you will check, is the value stored at this node equals to the value you are searching? Yes, and you will return this node, and you return this node, and this is our answer. Our search is successful, and we will exit, and we have find the element. This is how this searching procedure work. Now let us take a scenario where the element is not existing, and in that case how this means this algorithm will perform. Let us check. Okay, so let me clean this. Now let us assume that we are looking to find, let's say 26. 26 is something that we are looking for. Okay, so how to search? We will pass the address of the root node, and we will pass value equals to 26. So we were here. Now is this empty? No, this is not empty. So again we will be going to check, is this value is less than 26 or more than 26. So if the value which you are searching, the value is the this val is the value which you are searching. If this value which you are searching is more than the tree data, now this is the tree data. So if the value which you are searching is less than the tree data, then you have to call this procedure, that is tree left. So you have to move toward the left subtree. You will pass the address of this node. Now again you will check the value which you are searching is less than this or more. If it is less than this, then you have to move left. So because you are searching 26, which is less than this, you will pass the address of this node. Okay, now you are here. Now again you will check, is the value which you are searching is less than this or more than this. So the value which we are searching is more than this, it will pass the address of this node. So you are here. Now it will check the value which you are looking is more than this. Again we are looking for the value which is more than this, it will pass the address of right. So actually this node does not have a right child. So if you look at this, if you look at this node structure, this is the data field, this is the left field. Left field is actually containing the address of this node, and this is the right field. Now since right field has no child, so it will contain null. So now the value which you are searching, which is 26, which is more than this, so it will go to the right child, and right child is null. So now in the next call it will pass null. Now again when the call is made, and it will check that the value pass is null or not. If the value pass is null, that means your your element which you are searching is not existing, and you will return here, and you will return, or you can say the print not found. So this is how the search procedure works in the binary search tree. Now the next we will see that how we can insert any node into the binary search tree. Okay, so let's move to the next part. Okay, now this is an algorithm for inserting a node into the binary search tree. So we are having one procedure, we are calling it the insert, and here we need to pass the tree, which is actually the address of the root and the value which you are interested to insert. Now step number 1, if tree equals to null. If tree equals to null, it means the address which you have passed does not contain the address of any node, but it is null. Then what we will do, we will allocate memory for the tree. Now this situation can also be arised when there is no tree existing. So if it is occurring at the very first stage, that means there is no node existing in the tree and the tree is empty. That means you are going to store the very first node. You are going to add the very first node into that tree. If you are getting at the very first time the tree equals to null. Okay, so if the tree equals to null, then what is required? You need to allocate memory for the tree. You need to create a node. You are going to create a node for this tree and set the tree data equals to val. Then you are going to insert the value which you are interested to store. Now keep in mind we have three parts. One is the data part, one is the address part, you call it the right, and this is the address part for called left. So this actually stores the address of the left subtree. This it stores the address of the right subtree. Now, so whenever you are going to add any node, now one thing to always keep in mind that node are always be added as a leaf. Node, whatever the node you add, you cannot add any node as an internal node, but it will always be added as a leaf. And whenever you make any node as a leaf, that means there is no left and right child are existing. So this will always be required. You need to set the value into the data field, and you will set the left child and the right child equals to null. Okay, so otherwise if the tree is not null, means when you are going to insert any node and already the tree is existing, then at the beginning you will not get this situation, and then you have to check that the value which you are interested to insert is less than the root value and or the more than the root value. So if the value is less than the tree data, so the value which you are inserting is less than the tree data, then you are again calling this insert procedure and you pass the address of the left subtree. This is the same type of approach which we have seen in the search procedure. The only thing we have to keep in mind that here our objective is to insert the value, but every time we are using the same approach, if you are if your value is less than the root data, we need to go to the left. If your value is more than the root data, then you have to go to the right, and we are doing this procedure recursively. So inserting the tree left well, and otherwise if the value which we are inserting is more than the tree data, we are calling the procedure and working for the right subtree, and we keep on working until you go to the situation tree equals to null. Okay, so how this entire process will work in the real scenario. So we will take one example and we will realize that how we can make use of this algorithm to insert a node in the binary search tree. So we'll go for one example. This is one example. Let us assume that this tree is given to us, and this is our insert procedure, the algorithm that we have discussed just now. We will use this algorithm and you will see that how to insert any node. Now let's say we are interested to insert a node with value, let's say 38. 38 is the value which we are looking for. So you will call a procedure, you pass the address of the root, and also you will pass the value which you want to insert, that is 38. So you are here, right? Now since the this tree is not equal to null because already we have the tree existing. So as I told you that tree equals to null in the very first step or in the very first stage when the tree is not existing. Otherwise tree equals to null will be happening not at the first stage but at a later stage. So this is not equal to null. We already have a tree, and then we have to check that we have to move to the left side or right side by comparing the value which we want to insert. So we want to insert 38, which is less than 39. So we will pass the left subtree address. So this is the left subtree. So this address is being passed. Now again, this is we are having a tree. This is not null. So we will check that this value is less than 38 or more. So this value is less than 38. That means we have to move to the right. So it will pass the right subtree address. Again, this is not null, and it will check that 38 is more than or less than. So we will find that 38 is more than this. So it will pass the right child address. Okay. Now we reach to the situation. Now let us assume in this way, this is the data field, this is your right field, the right link, which is null, and this is also null because this is a leaf node and we don't have any child for this. Now you are here, and again this is not null, and you need to insert 38. 38 is more than this, so it will pass the address of the right child, and the right child is null. So now tree is actually pointing to null because you keep on moving from the root and you keep on moving and you reach to the situation where now tree is pointing to the null address. Now and the next time when you make a call, this condition will satisfy. Up to now we are working with the else part because it's keep on moving, and because this is not null. Now we have moved to the null part. So now what is required? You need to simply create your node, and you have to simply insert this value 38 and keep the left child null, right child null. That's it, and we have able to insert the value which we are looking to insert. So this is 38 inserted here, which has no left child, no right child. And also we have observed that all the node values are always inserted as a leaf. So whenever you insert any element, any node, any key value, it will always be inserted at the leaf. So this is the insertion procedure. Now we will take one more example and we will construct a fresh binary search tree. So let us move to one more example. Now this is your insertion algorithm, and we need to construct a binary search tree by inserting these following nodes. So the very first node is 39. So we don't have a tree at this point of time. So tree is actually null. So initially when you start working on the tree is null. That means there is no tree existing. Now when there is no tree existing, what you will do? You will create one node. You insert 39, the value which you are looking for, and then set this. So actually now you did this thing. Your first node is existing, okay, and it does not have any child. Then you want to insert 27. So when you want to insert 27, what you will do, you are passed with the root address, and then you will check that the value which you are inserting is less than this or not. So it is less than 27, so you will pass the left subtree address. So left subtree address is null here. So now it is null. You again reach to this situation, and what you will do, you will allocate one node, you will write 27, and then set the left and right subtree empty, and now this is connected to this. So we are able to achieve this. The next you want to insert 45. So again you will start from the root, and you will check that 45 is more than this. So you will pass this right subtree address. Right subtree address is null. So you will be in this scenario, in this case you have to allocate a node, and then you will insert 45, write the data, and keep your left and right child null. So we are able to achieve this thing. Then you insert 18. So 18 you start from here. 18 is less than this, so you pass this address. Now 18 is less than 27, so you pass this address, and this address is null. So again you are in this situation, and it will ask you to create one node, insert the value 18, and connect to this, and make the left and right child empty. So I believe that you have understood that how the algorithm is working. Now quickly we will insert this node, and we will see that what is our final binary search tree. So 18 will go here because 18 is less than 27. Then 29, so we start from here. 29 is less than this but more than this, so 29 will come here. Then 40 will be more than this and less than this, so 40 will be left child of this. Then 9, so 39, this and 9 will be here. Then 21, every time we have to start from the root node. So 39, 27, and we are looking for 21. So 21 means less than this, and you are here more than this, so here 21. Then 10, so we have to start from here, less than this, less than this, less than this, but more than this. Then 19, so less than this, more than this, and less than this, so 19 here. Then 54, 54 means more than this, and here. And then you say 59, so more than this, more than this, more than this, and this is here. And 65, so we start from here, 65 right child, 65 right, and 65 is here. And then 60, so 60 we have to start from here. So this is our last node to be inserted. We start from the root node. 60 is the value which is more than the root node value, so we'll go to the, it will pass the right subtree. This is again 60 is more than this, we move here. 60 is more than this, we move here. 60 is more than this, we move here. But 60 is less than this, so we will go here. So one thing to observe, that always we are inserting a node as a leaf, and this is how we can get the this is how we have constructed our binary search tree. So I believe you have understood that how the insertion can be done in a binary search tree. The next operation to see is a deletion operation. So we'll see in the next part.